So far, we discussed some stuff about dissipation and how to estimate it and how to calculate the exact value of dissipation. And let's have a review of this. There are some facts in these definitions. The first thing is that we were talking about dissipation rate, I mean epsilon, and we have shown that the order of magnitude of the epsilon is like this. So it's order of magnitude of epsilon is like this, and you know that the unit of the epsilon is meters squared per seconds cubed. And we know that this u prime in here is related to the order of magnitude of fluctuations, and you had this length L in here, which is related to the size of the large scale eddies. So large scale eddies, right? The energy, as we know, is getting generated at these large scale eddies, and then it gets transferred to a small scale eddies, as you see in this graph at the right. And finally, it dissipates into heat at the very, very small scales. The energy cascade, this energy cascade actually shows you how much kinetic energy you lose in 1 second. So it's actually the unit is meter square per second square per second. So in 1 second, how much energy? This is the unit of energy, meter square per second square. How much energy you are losing per unit of time. And this is the first thing that we know, the order of magnitude. And the second thing is that it's been observed for many years in different types of turbulent flow experiments. I mean, experiments concerning fundamental flow types or canonical flow types like jets, wakes, and etc. People have seen that this epsilon, the dissipation rate, does not change with Reynolds number. It means that if you are observing a free jet flow, if you measure somehow the dissipation characteristics for low Reynolds numbers, of course, it still has to be in a turbulent flow regime, and high Reynolds numbers, this epsilon does not change. We know that Reynolds number is a function of viscosity, right? And this means that the epsilon is independent of viscosity. And from the order of magnitude, we do not see it actually. So from the order of magnitude, you see the fluctuations, you will see the length. So you don't see the independency of viscosity there. The third fact is that if you look at the actual epsilon term, this is the actual epsilon, in turbulent kinetic energy equation, the term is 2 times nu viscosity times Sij bar. And this Sij, the bold S, is the fluctuating strain rate that I'm writing in here, Sij bar. And considering these three facts from experiments and theories, and also those assumptions that we have, now we see if epsilon is independent of viscosity, it means that viscosity does not affect dissipation. If viscosity goes to zero, we know that Reynolds number goes to infinity, right? Because you know Reynolds number is UL times nu, right? And if this goes to zero, Reynolds goes to infinity. Actually, it's not going to infinity. It goes to very, very large numbers, not necessarily infinity. In other words, in very high speed flows, viscosity tends to be zero. So what will happen to mathematical equation that you have in here? According to this equation, 2 times nu times Sij bar, nu goes to zero, but still you have to have a finite value of epsilon, which is independent of Reynolds number. This means that in order to keep this epsilon finite, when nu goes to zero, this Sij should go to infinity or very high magnitudes. Only then you can manage to have a finite amount of dissipation, which is observed from the experiments. So we are talking about instantaneous gradients in here, dui prime, right, dxj, and of fluctuating velocity components and actually it is in all directions because it's ui xj, and we take the square of it. So you see the square of it, and then we get average of it. So we come up with Sij bar. The question is for large Reynolds numbers where viscosity could go to zero, the term Sij. Sij should obtain a very large value. We just said this. And how can it be possible for, when you look at this thing? How can it be possible? We have two options, and these two options is either the fluctuations go to very large values, or the scales, the xj, the scales should go to very small values. So if one of those conditions happen, only then you have the finite value of epsilon at high Reynolds numbers. And we observed that these du primes, which appear on the numerator, cannot go to infinity, or when you look at the order of magnitude of these fluctuations, can it be as high as infinity? No, it cannot. And the reason is, if you remember, we have gone through some fundamental turbulent flows like these jets and wakes, shear layers, and stuff. And those are fundamental flows, and they occur in many engineering applications as well. In each of them, the order of magnitude of the largest fluctuations is related to, for example, velocity deficit in the wake or the centerline velocity in a jet, and so it's not infinite. So these du primes cannot go to infinity. So we only left with the second option, which is the fact that dx or length scale should go to very, very small values. This means that if you increase the Reynolds number, and if I make an experiment now, this is what I expect to see. For example, I have a jet with a low Reynolds number, but it is still turbulent flow, and I have a certain dissipation. I increase the Reynolds number either by playing with the jet diameter or with the velocity. For example, I make velocity 1000 times the velocity. And according to these results, what I expect to see is this. I have very high Reynolds number jet, but it keeps the same level of dissipation. Sorry, mm, just a second. I got it. It keeps the same level of dissipation, and we said that du prime cannot go to infinity, so the length scale should go to very small values. If I can somehow observe the eddy sizes inside the turbulent jet, inside this jet, I should see a very, very small scale eddies, which I shouldn't see at low Reynolds numbers. This was also proved by experimentation. So the question is, we know that the level of dissipation, this dissipation rate, is determined by the largest scales, right? We said that the level, the order of magnitude, is determined by the largest scales. So the smallest length scales in flow do have an influence as well on dissipation. We just said because of this dx, we concluded that dissipation occurs at the smallest scales, right? So the first question is, what is the smallest length scale in a turbulent flow field? Can we actually find this smallest scale size? not maybe the exact size, but their order of magnitude in general. That was basically what Kolmogorov wanted to do, to come up with a methodology to do this. He tried to answer what is the smallest length scale. Basically, he had two hypotheses, and the first one, which is known as Kolmogorov's first similarity hypothesis, says that in every turbulent flow at sufficiently high Reynolds numbers, the statistics of a small scale motion have a universal form that is uniquely determined by dissipation and viscosity. So a statistic here means behavior. For example, this Sij that you had before, Sij, the small Sij, fluctuation strain rate is it's a statistic because you are doing this Sij bar. This is the average process, so it's a statistics. And universal form, which Kolmogorov uh, mentioned, means uh, being regardless of where the flow is actually happening. This could happen within the cylinder wake, within a jet flow, in a wind tunnel, around the wing of aircraft, or in the nozzle exit of a rocket engine, or even in the atmosphere of Jupiter. It does not matter. Small scale eddies do not know where they are generated. This is called the universal form. They are not aware of what has happened before. So the starting point of this similarity hypothesis is that the fluctuations are a function of dissipation, rate, and viscosity. And then he started to do some dimensional analysis, like the epsilon is related to the L squared over T cubed. You know this. Here it is L squared over time cubed. And your viscosity, you know that it is L squared over time. And to obtain velocity dimension, in here to obtain velocity dimension, you should multiply these two. So epsilon times nu gives you L over T to the power of 4. So L over T is velocity, right? And he came up with this conclusion that the fluctuations, the order of magnitude of fluctuations is epsilon times nu to the power of 1 over 4. So this is another estimate of order of magnitude of these fluctuations that you have. From now on, we try to estimate the order of, uh, let's say, delta x or dx in the denominator that I just showed you. We need to estimate the order of magnitude of these. We know that epsilon is proportional to u prime cubed over L, and the mathematical relation is 2 nu times Sij bar. So epsilon is related to nu times du prime dx squared bar. And then you know that du prime, the order of magnitude of fluctuations, is epsilon nu to the power of 1 over 4. And when you do this mathematics, you will find that your delta x is actually related to this. So in here, u prime is velocity fluctuations of the largest eddies in the domain, and L is again the size of those largest eddies. And then if you rearrange everything in here, you will find that your after reorganizing, you will find that delta x over L, this is the smallest size, this is the largest eddy size, nu is your viscosity, u prime your fluctuations. So you will find that the smallest to the largest size is equal to Reynolds to the power of minus 3 over 4. So This Reynolds number is actually called turbulent Reynolds number because it is based on the turbulent fluctuations, U prime. And as I said, delta x is the smallest length scale, which we will call it Kolmogorov length scale in just a minute. You have to note that this Reynolds number is for largest eddies because it is written for U prime and L. Remember that U prime and L are related to the actual geometry of interest. You remember these from the previous discussions. And this equation in here, Reynolds to the power of minus 3 over 4, shows that the properties of the largest eddies determine the ratio of the size of the smallest eddies that can possibly occur in the domain to the size of the largest ones, which is L. So your delta x is proportional to this. We said this. So your delta x is proportional to L times Reynolds to the power of minus 3 over 4. And when I reorganize it, my delta x will be proportional to nu cubed over epsilon to the power of 1 over 4. This is exactly what we were trying to achieve as a result of Kolmogorov's hypothesis. Because Kolmogorov hypothesis told us that delta u prime, and um, therefore delta x should be a function of nu and epsilon. So we just found it. Delta x over delta t is also a function of nu and epsilon. And now we have this function delta x in meters that is just found it nu cubed over epsilon. So we call this as eta. We show this as eta and we call it as Kolmogorov length scale, this delta x, this small scale delta x. In other words, the smallest length scale is determined by viscosity of the fluid and the energy dissipation rate. Today, when we talk about the Kolmogorov length scale, that is the length scale of the smallest eddies that can possibly present in a turbulent field. From numerical calculations, especially DNS and LES, and also from experiments like PIV measurements, particle image velocimetry, you can actually measure what epsilon is in your turbulent flow field. And then you can estimate the smallest eddy size. So you had this relation before, delta x, and from here, this equation suggests that provided that you have an idea about the largest eddy, uh, L, in your domain and the magnitude of Reynolds number, okay, then you can still estimate the smallest eddy size, this delta x. This is useful especially when you are doing DNS, direct numerical simulation. We will see it hopefully in few weeks. DNS means solving Navier-Stokes equations directly without any need for any turbulence model. So solving instantaneous flow equations, not averaged equations, instantaneous ones, by using enough number of spatial resolution and a small enough time steps. So if you want to do that kind of simulation, the question is how small your grid should be. You're doing numerically, you're doing it numerically. So you have to put a grid. So this tells you actually how small this grid should be. Then this equation will give you an estimate of that smallest grids. Delta x over L is equal to Reynolds to the power of minus 3 over 4. If you're trying to simulate a turbulent combustion field in a combustor by knowing the general geometry of what you are going to simulate, you can estimate the order of largest eddy sizes and then estimate the order of largest fluctuation levels, and then you can estimate the order of smallest length scales. So your grid should be in the order of magnitude of that in order to resolve those length scales. Of course, you have to do an unsteady simulation because there is no such thing as a steady flow. And unsteady simulation means you have to resolve at time as well. The one thing is resolving in space. Another story is resolving in time. So what should be your smallest delta t then? So yeah, it should be small enough to resolve the smallest eddies as well. You will need a time scale of these smallest eddies. And in order to estimate the time scale, you have to introduce some new parameters. Um, First, we introduce the ratio of velocity scale um, of the smallest eddies to the velocity scale of largest ones. So this is called U eta. So eta, you had your eta. This is the length. So this is in meters. The U of eta is it's the velocity. So it's meter per second. This is the velocity of these eta scales. So how do you find it? It's epsilon times nu to the power of 1 of 4. So this u eta over u prime, which is the ratio of the smallest to the largest scale velocities, will be the Reynolds to the power of minus 1 over 4. And since we have now a velocity scale, u eta, combining the length and velocity, I can find the time scale of the smallest scales as well. So I call this as tau eta, and it will be in the order of Reynolds to the power of minus 1 over 2. So we now defined three important ratios, right? This equation, and this equation. And after, I mean, there are no smaller eddies than these smallest ones. These are the smallest ones. They cannot get any more smaller because viscous effects at these scales, at eta scales, are very dominant, and everything will dissipate after this. Everything will dissipate to the heat.